Hello everyone, welcome back to another SLHL 2025 IB chemistry video. This will be the last video on the structure topic, and in the next one we will start looking at reactivity. And today we're going to be looking at ideal gases, laws, assumptions, and equations that you'll need to know how to use and manipulate. So, let's start by looking at the ideal gas model and what it assumes. So there are four main things that the ideal gas model assumes, and the first is that the intermolecular forces between particles are non-existent. Secondly, it assumes that the volume occupied by the particles themselves, so particle volume, is also negligible. Next up, it is assumed that any collisions between particles or the walls of the container in which the substance is being held undergo elastic collision. This means that it's assumed that no energy is lost to heat or transformed into any other form of energy from Ke, kinetic energy. So it's assumed that none of this Ke is ever lost. And finally, it is assumed that there are obviously multiple particles which are in constant motion. So let's look at the limitations of this ideal gas model, because as we can see, there really are some things that stand out that just tell us that this may not apply to all situations. So limitations start to shine through at more extreme conditions. An example of this would be at a lower temperature. At a low temperature, particle moves more slowly, which means that the intermolecular forces are more pronounced, meaning that they are more relevant or act more in a way that really distinguishes the properties of the gas, changing it from this ideal gas model. And it is for this reason that condensation occurs, because particles will start to move more slowly. There will be more forces between the particles, resulting in this. And next up, another condition in which the limitations really shine through are at high pressures. So at a high pressure, yet again, the particles are closer to each other, which means that intermolecular forces are also more significant and also alter the gas's properties. And at high enough pressures, the volume of the particles can no longer be considered negligible, because they're packed so closely together. Finally, let's look at our gas law equations. So the first that you will need to know is PV equals nRT. Here P stands for pressure in pascals, volume, well, V is volume in decimeters cubed, N stands for moles, R stands for the ideal gas constant, which is equal to 8.314 joules per Kelvin mole. And finally, T is our temperature, and this will be in Kelvin. So you will need to know how to apply this formula to different situations, keeping in mind the conversions that may or may not be necessary in order to plug things into this equation correctly. And finally, let's look at the combined gas law. So Boyle's law, or in other words, P1V1 equals P2V2, assumes that a gas's pressure and volume are inversely proportional. This is true, or this can be used when temperature is constant. So you need a constant temperature. And Gay-Isaac's law, or P1 over T1 equals P2 over T2, suggests that temperature and pressure are directly proportional. And this is assuming that volume is kept as a constant. Now, if we take these two gas laws and combine them together, we will get the combined gas law, which is P1V1 over T1 equals, surprisingly, P2V2 over T2. So it's pressure times volume over temperature. Now that is all for this topic. Hope that was helpful, and that we will see you in the reactivity series.